All right, so I want to mention that on the multi-objective mini projects, I was really impressed by them. In the past, this first semester, I've done these mini projects. In the past, Pareto optimality has been something that has been a difficult subject for people to sort of grasp. And pretty much every mini project, everybody had a great problem formulated, found a Pareto frontier, found maybe several Pareto frontiers in some of the submissions, some of very interesting frontiers with gaps in them, things like that. Interesting explorations. So I was really impressed with them. I think everybody's submissions. I think I can say that literally. Everybody's submissions I was pretty impressed with. So great job on that multi-objective one. In not necessarily the most obvious concept, Pareto optimality, but I promise you that sometime in the future, maybe even near future, it'll become a useful concept for you. And so it's cool to see those submissions. So thanks for all your efforts on that. So we left off last time, introducing neural networks and giving kind of the biological background. And we had just started talking about this simple model of a neuron. So say recall something which I'm going to call and I'll put single layer perceptron. And a perceptron is, which we might abbreviate SLP. And a perceptron is a type of classifier. So in the single layer case, it is a binary classifier. And all that means is given a data set of features, then the perceptron's task is to classify whatever is presented to it as being either in one class or another. So binary in class 0 or class 1, binary classifier. When we get to multi-layer perceptrons, then that allows us to go for more than 2 classes. And so it's just generally a classifier. But for now, we just have this single layer perceptron, so this binary classification problem. And the way we drew that is basically this network, which I'm going to draw a constant, like a literal 1 as an input with a weight B. So coming out of this little gain, we just have B. And then we have all of our feature vector. So we'll have like an X1, an X2, X3, and so on, down to say Xn. And each one of them has a weight, W1, W2, W3, and so on, all the way down to Wn. And so coming out of here is just the multiplication of those. And all of those get summed in sort of the summing junction here. And then the output of that sum, which is just, again, the sum of all of the weights. And so I guess I'll put the B out front. So it's just the bias term. So I'll say these here are the so-called feature vector. Which I'll maybe write as X vector. And the output here is just the bias term plus all the weights from 1 to n. And then those things go into an activation function, which today I'll use A for that. And I'll say A of, and I'll do X bar. So I'll call this thing X bar. And this here is our activation function. And last time we talked about that this activation function could be a wide range of different things. For a perceptron, for a binary classifier, we're just going to use the Heaviside step function. So for binary classifier, perceptron, we're going to say that A of X bar is equal to just 1 if X bar is greater than or equal to 0, or so 1 if X bar is greater than or equal to 0, 0 if X is less than 0. And that is going to be equivalent to saying that this is 1 if this the sum is greater than the negative bias term. So I can say, I can write this sum here as, I'll say, W vector transpose X vector. So this is like a dot product. Or if you prefer, W dot X dot. And so this perceptron, another way I could say that is it's going to be equal to 1 if the dot product W transpose X is greater than or equal to negative bias. It's a 0 if W transpose X is less than the bias, less than negative bias. All right, so that, and this whole thing here is a mimic of the, if we were to redraw the neuron, see if I can draw a little better here. And so this is, these here are like the dendrites, and then the output there is like the axon, and the activation function is a little bit like an action. Then the activation function here is a little bit like an action potential. So that's where the bioinspiration comes into play. But I just want to emphasize that this is just an abstraction. When you actually implement an artificial neuron in software, you don't build an architecture that looks like this traditionally, you just implement the math. And so really all an artificial neuron is inside this, inside the computer, is just this activation function operating on this sum of the bias term plus the weight vector times the feature vector. So internal to the computer, it's just a little vector multiplication and an addition, and we can find that we can actually, if we generalize the feature vector to include a 1, then we can have the weights include the bias term, and it's just an activation function acting on a dot product. We can model it, you know, abstractly as this sort of structure that kind of looks like this neuron down here, but it's really just that up there. And that thing up there is really just a generalized linear model. All right, so that's basically where we, I think, left off last time. So any questions about this basic idea that you're inspired by, this idea that neurons can be connected together to compute? When you model the neuron, you get this kind of structure here where there's a bunch of things that sum up together and trigger an activation function. But then once you kind of write this all out, you see that this kind of simple model is really just this mathematical function up here, which we can easily implement in a computer doing, a bunch of matrix operations and things like that we know how to do inside a computer. And we're going to gradually link more and more of these things up together, which are just going to be, we're going to make functions of functions of functions. So we're just going to have, functions chaining into other functions. But we are going to abstractly represent them as these layers that we'll get into here today. But I don't want to give you the impression that the traditional way you actually implement a neural network is to create like a bunch of these little, neurons that are wired together. In the end, it's just math behind it's just this simple math, these functions that are chained together. Maybe even a lot of them, but usually not a lot of functions, but very high dimensional vectors just adding together. So any questions about that so far? Our next step is to interpret what the heck is going on here and how we actually use this to do binary classification, and then grow it into something that allows us to do more sophisticated things than binary classification. All right, so this is, again, probably review for a lot of you who've taken some machine learning courses. But hopefully I'll try to make things more interesting as we get into some embellishments here. Okay, so that's our basic neuron, binary classifier, perceptron. So what we would like to do is just decide where in the notes I want to fork off. We ended in a funny spot. Okay, this will be fine. All right, so let's think about what's actually going on here. So I've mentioned that these weights, that all I'm doing is this kind of dot product here. And so if I was to imagine a space, so let's say I've got a simple feature space. And so as an example here, this is let's say my feature vector has two components. And let's say I've got a data set on automobiles. And in this data set, one of the features, X1, might be the car speed. And the other feature, X2, might be the car size. And so every point represents how fast the car can go, maybe its top speed, and how big the car is. And so I could put a bunch of these points in here, and I might get some that are down here. And I might get some that are up here. Maybe I'll draw them in a different color. Okay, so I've got these different cars, and so each one of these points is a feature vector. Where this is, speed, and this is maybe top speed, and this is size. All right, so what I would like to do is figure out which cars are the imports and which cars are, say, the American cars. We're talking about cars in this market here. And so it may just be that these are the imports and these are the American cars. Maybe, I don't know, something along those lines there. And so what I would like to do is feed my perceptron some data points where I know for sure that like that either this is an American car and this is an import. So I've got these two categories, so these two classes. So I guess I can place it here. I've got two classes. And those are American cars and imports. And so I want to train this neuron to be able to look at the feature vector and then make a decision as to, do you predict that this is an American car or an import? If I give you the speed, the top speed, and the car size, then you know, which one is it? And so how do I do that? Or what's going on here? Well, we think of each one of these feature vectors as an X. What I'm trying to do is train the weight W so that the dot product gives me an indication of which one's kind of which here. So if I think about an individual X vector, so like if I were to draw a line out to one of these, so here's some X vector. The weight vector is another line in this space, and the dot product is kind of a projection of one onto the other. So if I were to put a weight vector, I'll use a different color here, like let's say this is my weight vector, then the dot product between these two, it's kind of related to the angle between these two, but you can kind of think of it as projecting one of these onto the other. And so it's the dot product is a little bit like taking the shadow. It's like if you were to shine a light that was going this direction, then the shadow of the X vector on the W vector kind of gives you an impression of what kind of sort of the dot product is here. And so if they are collinear, then then you get kind of the longest shadow. If they are 90 degrees out of phase, then when you shine that, you don't get anything on there. So when two vectors are 90 degrees out of sync, their dot product is 0. When two vectors are collinear, their dot product is maximized. And so if I think about this, I can think of any weight vector as a kind of a measuring stick. So for any weight vector, then if I were to measure this vector down here, then I get this far on the measuring stick. If I were to measure this vector here, I get this far on the measuring stick. If I were to measure this vector out here, I get this far on the measuring stick, and so on. And so taking the dot product is just measuring along a ruler that's in this direction. So if my points are aligned in a certain way that we say is linearly separable, and I'll write that down in a second, then all I need to do is choose a weight vector whose angle is just right. And if the angle is just right, then the dot product, then I just need to choose a bias term that tells me how much along that angle do I need to get me into one class, otherwise I'm in the other class. So like this weight vector, if I look at it, I can see that, actually there's, maybe I'll go to my highlighter. There is sort of a plane that separates these points. And that having that plane we refer to as being linearly separable. So we can say a plane separates points from each class. And so in theory, I should be able to find a weight vector that's perpendicular to that plane. So I just happen to draw this weight vector and it's almost perpendicular to that plane. So, I mean, for convenience, maybe I'll say that it is perpendicular to that plane. So I'll say here that this is weight vector is perpendicular or orthogonal to the separating plane. And so if I can find that weight vector, then all I need to do is define a bias term, and that bias term tells me where the plane is. So it's kind of like, you know, this point right here, that point corresponds to a certain bias term B. So if I can get the angle right and choose the bias right, then I now have a mathematical way for me to separate this up so that points that when their dot product is less than that bias term, they will be under the plane. When their dot product is greater than that bias term, they will be above the plane. And that's how a binary classifier works. So that's what's going on here. So I just need to say that, you know, in theory, you know, so the goal here, find W, which is an angle, and B, which is a magnitude that separates two classes, where I got W dot product X is greater than or equal to, and I've got this as negative bias right now. All right, so that's how a binary classifier works. We just need to find a way to find that W. And you say, well, how do I find that W? And I'm going to give you an algorithm to do that, but already you can start, I mean, the whole front half of this class has been about optimization and all that. So we're effectively trying to find the optimal weight vector and bias term to have maximal separation here. So you could imagine penalizing wherever this decision is incorrect, and then minimizing your penalty. And so you could imagine a genetic algorithm walking through all the possible weights and all the possible biases and finding the weight bias pair that for all of your training data gives you no penalties. So for all of your training data, it will ensure that all the blue points map to a 1 and all the green points map to a 0. And that's effectively what training neural networks do, is exactly that. It's just finding the weights and the biases that minimize the penalties for getting decisions wrong. Okay, so questions about that? Do we see the geometric interpretation of what's going on in the single layer perceptron? Okay. All right, so like I said, we can, oh, I see a question online. It's a plane, not a line. So the highlighted thing that I've got here, this cyan here, here it's a line, but in general, we're talking about a multi-dimensional space. And so in general, it's a plane, but, you know, so it's a linear object that it's perpendicular. The important thing is it's perpendicular to the weight vector. So it is technically a plane, but it's a plane coming out of the board. And so we only really care about it being a line in this space. But if I generalize to feature spaces that are more than two-dimensional, then it will be a plane. And the reason it's a plane is it's one more dimension than a line. And so a plane is defined by a vector. And so the weight vector is the key component of the artificial neuron. And so the weight vector is actually defining a plane. And that's why we need linear separability, because if we're only using the weight vector, then we only have a plane available to us. And so we need data that you could put a plane in here, and that plane would separate these two clusters. So I drew it as a line because I'm two-dimensional, but imagine three-dimensional higher, and it's a plane. Okay, good. All right, so any questions about that? All right, so a simple way that you can train these things. So I'm going to, a simple generalization. I'm going to absorb bias into weight vector. And so that just means that my feature vector takes on a 1. So imagine that I've got my normal feature vector. So my feature vector now is going to be, I have an x0, which is going to be equal to 1. And then it's going to have my x1, x2, all the way up to xn. So this is my traditional feature vector. And then by doing that, then I can have a weight vector w, which is equal to, has a w0, which is the old bias term. I'll just start w0, w1, all the way up to wn. And so this here is the bias term, and this here is the traditional weight vector. And then from there, by doing that, then now all I really care about is whether the dot product is greater than or equal to 0. So, so with here, my activation function will be that. So remember, my activation function is the Heaviside step function. So the output y, which is equal to the activation function times x bar, is going to be equal to the activation function of w x, which will just be 1 if the dot product is greater than or equal to 0, and 0 if the dot product is otherwise, which is basically equivalent to saying that the cosine is positive, right? So if the, this is like saying angle between minus 90 degrees and 90 degrees, or cosine positive. So by absorbing a 1 into the feature vector, then I basically now have a feature space that it's a linear feature space. It's kind of always of going through the origin, and so I'm trying to find an angle, and all I care about is anything that's 180 degrees on one side of that angle. So it's kind of like, now that I've got this this feature space with my x0, my x1, my x2, and so on, then that plane is always going to pierce the origin. And I'm trying to find an angle, w, And the one class is always going to be in this 180 degrees. And the other class will be on the other side of it. Okay. All right, so that's our generalization. So how the heck do we train this? Any questions on this? I just was trying to make it easier so we don't have to have this bias term floating around. So there are a bunch of different ways to train, but I'm just going to throw out a simple one before we get into the more sophisticated ones that generalize to even other types of networks. And this, again, you could imagine also using a neural network, using a particle swarm, whatever, but this little simple arithmetic way will work so long as your data are linearly separable. So the steps to train a binary classifier or a single layer perceptron. One, start with random weights. So random initial weights. So that's your weight vector W. And then two, then we're just going to run a recurrence relation, or we're going to iterate through where we're going to say for every weight, we'll run this expression, Wi at the next step of the optimization algorithm, or the training algorithm, is the previous weight plus the dot product minus the desired output, and I'll write this in a second here, times the component. So I'm going to define this as, yeah, I'm sorry, when I wrote that as yi, I meant to write that as yj, and I've got, j is going to be my index of my training data. So this is yj here, yj, xj, and this is going to be xji. And this here is either 0 or 1. And this here is the jth feature vector from training set. And this up here is the jth desired output for input xj. And so this thing is just the ith component of xj vector. So the idea is we've got a bunch of training data that looks like x1, y1, where maybe that's equal to 0. We've got an x2, y2, which maybe is equal to 1, all the way down to some xm, ym. And so these are all desired inputs and outputs. And so in the training process, this really simple training process, and the order of this doesn't really matter too much because of the linearity of this, but basically we're going to iterate through every weight and every component of every feature in our training set, every feature vector in our training set, and we're going to calculate, this is effectively a type of error. So this is sort of an error function. And so remember that this Heaviside step function, the way we've defined it, we're really focusing on whether it's greater than 0 or less than 0. So this thing sort of ends up generating a type of error, and that error will cause the this component to change. So there's this weight vector is going to increase or decrease based on the direction of the error and the scale of the error. And so this xji, which is the component from the training, acts as a type of step size. And so it's so this looks a little bit like a gradient climber, but it's a little bit more of a heuristic here. But we can show that if you apply this across every single weight, across every single feature, and across every single component of those features, then you'll end up getting a convergence to a weight that separates the data, so long as the data are linearly separable. We could imagine data, which I'll show in maybe a little bit here when we talk about radial basis functions, that like looks more donut shaped, where the two classes are like, there's like a class that's sort of out in the middle of space, and everything around it is the other class, where I can't use a plane to separate those things up. This won't work for it. But if there exists a plane that separates your data, then a simple algorithm like this will find that plane, and that plane will be characterized by the weight vector. All right, so any questions on that? I'm just here, this isn't, modern neural networks will use something called back propagation to do, or basically gradient finding or gradient descent to solve this problem. And that's what we'll get to. But I'm just showing you that there exists relatively simple ways that can converge to solving this neural network. And I also mentioned that the neural network is basically just regression. This is a little bit like logistic regression. And so there are plenty of other ways you can fit these weights. If this is a relatively small weight vector, like, it's not a very high dimension, you can use standard methods from statistics to sort of do a best fit line. That's really all these weights are, is the slope of a giant best fit line. And so if the dimensionality is small enough, then you could just use all the methods you learned in whatever undergraduate statistics to do kind of a least squares problem, where you do a least squares, with these linear weights, and you end up getting the exact same thing. So, but this is a way that should work for any size vector. You just do this iteration until eventually it converges and you stop, and then you're set. All right, so that's our binary perceptron. It will work for these linearly separable spaces. Okay, so any questions about that? Okay. All right, so not everything's linearly separable. Not every decision problem you want to do is going to have linear separability. So what about, what about when things are not linearly separable? For one thing, or in general, what happens when we have nonlinear relationships between variables that we're interested in analyzing? Well, there is a slight modification on what we just talked about, and that is the radial basis function neural network. Or RBF neural network. Or RBFNN. And so this is inspired by neuroscience as well. And it's this idea of that there are these receptive fields of sensitivity in the nervous system. And so this is sort of the idea that you might have, let's say, sensory neurons in your skin that only are responsive to a small area of space on your skin. Or, so there's a small receptive field where if you get close to it, then they fire, but as you move away from it, then they don't feel that. So they're very localized. And so there's a bunch of these examples where you've got specialized, for your sensory system is not paying attention to all inputs. It's really paying attention to a small set of inputs. And so that basic idea, we can take a structure that looks like the structure we were just using, and we can add these receptive field units that can give us the ability to reshape the space so that effectively the same machinery that allowed us to do linear classification will allow us to do nonlinear classification and other things. And the way that looks like is I again have my inputs, my feature vectors, or my feature vector. So it goes up to whatever, xn. And what I'm going to do is introduce these things, which I'm going to draw a little icon of kind of a hump, kind of a little bell shape. You can think of it as if you like, a bell curve. And each one of these are going to take inputs from all of the other inputs So imagine me drawing lines from everywhere to everywhere here. I already drew that one. So I don't know if I did all the right ones, but you get the kind of the idea. All the X's, each one of these receptive field units takes inputs from all of these X's. And I'll tell you what the receptive field unit is in just a second. And then these receptive field units, they then get summed up in a sum junction, just like we've seen before. And then the output here could go to an activation function. I'm not going to draw the output, so you could say there may be an activation function here. Or I can just assume linear, say, or I'll say, or just linear. And for now, I'm not going to worry about the activation function. All right, so what do the heck these radial basis functions look like? And so a radial basis function R, and I'll call this Ri, so we could call this one like R1, this one R2, this one Rn. What is it? I'll say Rm, because I don't actually need this to match. Like I could have a different number of radial basis functions than inputs, all right? So this radial basis function Ri takes X as a vector, and this is just going to be some kernel function, I'll talk about that here in a second, which takes as an input some distance. And so this could be, a norm, and this could be a two norm. So, Euclidean, Mahalanobis, etc. And this function here is often taken to be like a Gaussian, so think exponential, or a logistic, or otherwise. But the point here is that as you get, and then there is this center here. So each radial basis function, this CI is a parameter that is the center of the receptive field. So basically, for each one of these radial basis functions, there's a distinguished point in space where they are most sensitive. And as the feature vector gets farther away from that central point in space, the radial basis function's output falls off. And so if your feature vector is exactly the same as the center for this one, it will be at its maximum value when it passes out to this sum junction. But if you are way far away than that, then this one might be equal to 0. So that's the reason why we kind of draw these as kind of these bell-shaped curves. I don't know if you've ever looked really long and hard at the Gaussian or look at the Gaussian distribution, the normal distribution, but you know, as kind of an aside, I mean, let's think about the PDF for a normal distribution. And it's basically, you know, f of a normal distribution is proportional to, I'm not going to worry about the normalization constant, it's proportional to the exponential value of x minus mu squared over sigma squared. Maybe there's a negative out front there. All right, this is me off, you know, on the fly. This wasn't actually in my notes. So, you know, it's kind of like me. I hate doing numerical math unprompted because I know I'm going to get something wrong. So, but I think I got this right. And even if I didn't get this right, the spirit of what I'm going to say is going to, like, even if I got a minus sign wrong or whatever. But the point here is that a normal distribution is just an exponential decay applied to a squared distance. So in a normal distribution, what you've said is there's a special point, mu. This is kind of a center of a distribution. And as you get farther away from the center of that distribution, the probability density falls off. So if I were to plot the distance away, so if I were to plot, you know, x minus mu squared, you know, so it's just a squared distance, and yeah, maybe it's scaled or whatever, then all this is saying that is this, as this distance, as you get farther away, this is distance from mu, then you get an exponential fall off. But of course, we never plot this. What do we plot? We plot x. And when we plot x, then you have a mu here and you get a bell curve. But it's identical. The bell curve you get, this is the bell curve. The bell curve you get out of a normal distribution just comes from the normal distribution effectively being defined as an exponential decay with an energy function, which is, I mean, that's effectively what this is. This is saying that, like, the lowest energy state is when you're sitting at the mean. The highest energy state is when you're farthest away from the mean. So again, going back to kind of the Boltzmann distribution, then as you get, you know, it's very unlikely for you to be very far from the ground state, from the lowest energy state. And so you get a Boltzmann distribution at maximum entropy, which looks like this. But if you turn it back into the x space, as opposed to the distance space, then it turns into this down here. But it still kind of makes sense, because what we're saying is that's the reason why the normal distribution is symmetric, because it's all based on distance. So in the normal distribution, they're saying it doesn't matter if you go one standard deviation to the right or one standard deviation to the left, you get the same fall off in the probability. That's where that comes from. And so this is an example of a radial basis function. It's a radial basis function because as you radiate away from the center, it gets smaller and smaller. So it's can also be, you know, so we can call this a, you know, example radial basis function. And then this is also, you can also call it a kernel. Okay, so you can think of a bunch of different ways to define these radial basis functions, and they basically come from taking something that looks like this, where as you go from one distance to another distance, you go from high to low or low to high. So like in a logistic, when you're at zero, it's zero, but as you get higher, it goes to one. Well, you can imagine that's kind of like the same sort of thing here, where if I applied a distance into the logistic function, then at small distances, the logistic would be zero, but at large distances, it would be one. So it's a way of promoting areas or demoting areas, but radially so that if you get farther away from them, you either increase the penalty, or as you get farther away from them, you decrease the penalty. But the point is there's a center, and as you get farther away from it radially, you're affecting either adding penalty or adding reward. And so that's what you do in radial basis functions, is you put these functions here, like a normal distributional logistic or whatever, and each one of them has a center. So each one of these corresponds to, has a function associated with it and a center. So there's a function and a center, a function and a center. And then so all those things get added together, and they can get weighted. And so I can imagine, I can put like a B1 here, a B2 here, a BM here, so that what comes out of here is that the output here is going to be equal to the sum of the weights BI times the radial basis function RI of the X vector. And this right here is a radial basis function neural network. Now this feels like a single neuron. And so how am I justified in calling it a neural network? We're about to get there. But for now, just trust me that this expression here is a radial basis function neural network. And so what does this allow me to do? So I'll just highlight that so that it's clear here. All right, so before I go on, are there questions about that? Do we see where this all comes from and what I mean by radial basis function? So we just took the feature space, so that's our feature vector. This is a reminder, this is X hat, X vector, it's our feature vector. And we take our feature vector and we push them through these radial basis functions, effectively saying, how close are you to this point? How close are you to this point? How close are you to this point? And then we take all of those closenesses, we weight them, and we get this here. So we are going to train the trainable parameters are the weights and the centers. I think I got all those. Yeah. Maybe I'll do a different color. So these are the trainable parameters. Okay, so whereas in the standard perceptron, we only train the weights, we have weights that we're training, which are these weights, which I've labeled B1 through BM. We also have these centers. Now, how you train these things gets more complicated. A lot of times people use clustering methods to generate the centers, and then they use methods similar to what you'd use for other methods to train these weights. You could also imagine, again, using a genetic algorithm. Now, you've learned tons of metaheuristics right now, so I don't need to go in to all the different ways here. You could use simulated annealing, genetic, whatever. I mean, it's to choose all of these different these vectors here. But what the heck are you doing? Well, the idea of what you're doing here is, if I were to imagine, for example, a non-linearly separable space. So let's say, just as a simple case, I wanted to classify two groups. I've got a group, so I've got my, my X vector, X1 and X2, and I've got a group here, which are class 1. And then I've got another group out here, which are class 2. Now, it is not possible for me to separate these two classes with a plane, with a line. And so I would still like to be able to train my neural network to learn this donut, so that anything that was in the outer ring, it would call class 2, it would call imports. Anything in the inner ring, it would call American cars or something like that. And so how do I do that? Well, what the radial basis function does is it allows us to reshape this space so that the reshaped space is linearly separable. That's one way to say it. It might be simpler to say, well, what if I just create a center? So maybe I'll put this, imagine I've got a center here, and maybe another center here. And so this here I'll call my C2 vector, and it happens to coincide to my C1 vector. And this C2 vector, maybe I've got a Gaussian radial basis function, and this C1 vector, maybe I've got a logistic radial basis function. And so the idea here is if points are close to C, or did I get these backwards? I'm sorry, I got those backwards. So this blue one, the blue one here, I'll just erase the examples here. So the blue one, I want to demote points inside the circle. So the blue one maybe looks like a logistic radial basis function, and the purple one maybe looks like a Gaussian radial basis function. And so the idea here is if points come in and are close to the center, then those points will end up causing the R1 radial basis function to fire and have a very high number. If points come in and are far from the center, then they will cause the C2 radial basis function to fire. So, so this radial basis function effectively created a hotspot where only one radial basis function fires close to the center, and only the other radial basis function fires when you get far from the edge. And so that allows me now, if I look at the outputs of these things, these now become linearly separable, because basically if R1 is really high and R2 is low, then it must be the inner class. If R2 is really high, but R1 is low, it must be the outer class. Another way to view that, if I want to do the same thing, so that's one perspective. So if I'm going to just redraw the exact same thing, but just to keep it a little cleaner, I'll put it on another page. So again, X1, X2, I've got my blue points around the outside. I've got my red points in the middle. If I want to use all Gaussian activation or radial basis, if I want to use all Gaussian radial basis functions, then I could actually imagine building many of them, and I could have maybe an R1, which is centered in this area, an R2 in this area, an R3 in this area, an R4 in this area, R5, R6, R7, and basically I'm painting the space, whatever, R9. And so each one of these are Gaussian radial basis functions, but they have like a little domain. And so I can basically say that R1 corresponds to class 1, and R2 through R9 correspond to class 2. And so points come into here, and if they're in the center, they'll only excite R1. And if they're in the outside, they'll excite any of R2 through R9. And so this allows me to cover the space in an arbitrary way. So with as many radial basis functions, I can eventually just create little jigsaw puzzles where I can assign different pieces to different classes. And so I can cut up the space in this way so that when I come out of this, then the output of all these radial basis functions provides easy separability, where I could then apply an activation function, and that activation function, I could apply weights. Remember, the weights then get applied to these things here. So those weights become a separating matrix, which allow me to pick out one area over another. And that's how I can do my separation. So this is an input transformation that restores linear separability to data sets that are not separable, not linearly separable. It also just generally allows me to approximate a wide range of nonlinear functions. So before I go on with a riff of that, are there questions about this? Does everybody see what I mean by this? Is that I'm creating these distinguished areas, these little potential functions that are centered on space. I see a question online. The question was, so the first question, where does B fit in RBFNN? So I just used that B there as a weight. I should have used W there, but this wasn't meant to necessarily be a bias term here. Yes, you can add a bias function in the same way we did with a perceptron, and that's totally fine to have that bias in there, and that helps this thing do its job by having that bias as well. So I called these B's, and I don't actually remember why I chose to make the weights B's here, but if it's easier for you, they could just as well be W's. So those are just weights in front of the radial basis function. The other question was, could the spread in the radial basis function also be viewed as a trainable parameter? And yeah, you could add an additional degree of freedom where you could put a sigma inside here, so you could actually be scaling, so you could put a trainable weight inside here. So that's definitely something that you could do. So that's an option here. So typically with radial basis functions, at a minimum, we train the centers and we train the weights when we recombine them. And but yeah, if you want, it becomes difficult there because again, it's easier to pick centers and then use kind of linear methods to solve for the weights. Once you start getting into like choosing the widths of these functions, then you really need like a crazy optimization metaheuristic. That's where you really do need the particle swarm optimization and so on. But if you keep it simple to say, I'm going to use some clustering methods to choose my centers, and then from there, I'm going to choose my weights. A lot of times the weights kind of are good enough that you don't need to include your spread. If you just like increase the weight enough, the little bit of spread that comes out of the radial basis function that's in the close neighborhood is kind of enough for that. So if you got enough of these, so enough radial basis functions, you usually don't have to worry about training the spread of them as well, but you certainly could. It just makes training more complicated. I think that's the last question there. So any questions in class? Is this pretty clear, this modification here? All right, so like I said, so these radial basis functions, they can be used, sure, for non-linearly, I'll say for non-linear classification problems, but they also can be used for function approximation. So in other words, let's say, for example, you have a simulation that maps inputs to outputs, and you don't have a mathematical expression that models that simulation. Well, you can take a bunch of the inputs from your simulation and a bunch of the outputs and train a radial basis function to approximate what the sim will give you. And this is actually what goes on in a metaheuristic called surrogate optimization. And this is another metaheuristic approach. And so you can go into most modern professional numerical tools that have optimization toolboxes, like MATLAB. Like MATLAB has a surrogate optimization function. It's called, I forget what it's called. I think it's called surrogate. And what surrogate does is they take usually a relatively simple meta-heuristic, similar to a genetic algorithm, but usually something even simpler than that. And it will evaluate a very costly function. Let's say it's a simulation that takes 10 minutes to run the simulation and get an output. And it will run those as it needs. But over time, it takes all of the inputs and outputs that it finds, and it trains an RBFNN in the background to approximate your function. And then it will then use the RBF to guide intermediate optimization steps. So the hope is that over time, the radial basis function becomes such a good surrogate for the costly optimization function that you can just optimize the radial basis function. Now, of course, the radial basis function is not going to be perfect. So, it constantly goes back and forth. And so it periodically uses its radial basis function to kind of guide, new innovations, and then it will go back and then run the costly optimization function, see how well it did, and if it did terrible, then it'll run the costly optimization function for a while, and then retrain the radial basis function, and then as the radial basis function gets more and more aligned with the optimization function or with the optimization objectives, it can just use the radial basis function, and it's a much faster way to do that optimization. So surrogate optimization actually makes use of these RBFs. And then there's a bunch of other kind of similar things like time series prediction. So in that case, you can feed it a value as an input and give it the next value as an output. And over time, it will predict. It can do a good job at when you don't apparently see a pattern. So this is basically for finding patterns in time series data. And this is particularly good for those who work with chaos, where you've got what appears to be noisy data, but actually every point is predictable from the point before it. It's just predictable in a way that is hard to understand. And so these radial basis functions, if you have chaotic data, then these radial basis functions can do a pretty good job of predicting. And if you found like, wow, I thought this was noise, but it turns out my radial basis function neural network can predict the next point 99% of the time, then that tells you that actually there's this apparent noise has structure, and that structure has been captured by the radial basis function neural network. So they're extremely flexible little tools, the radial basis function neural network. All right, so in the last minute here, I just want to open up, kind of like where we're going to go next. And I just wanted to point out that when I originally drew the radial basis function, I kind of said it looked a little bit like a single layer perceptron, but I was calling it a neural network for some reason. And I said, I've got these R1, R2, all the way up to an RM, and maybe there's more or less of them than the inputs, and all of the inputs go into each one of them, and so on. And then these come together in a sum here, which generates an output. And that's basically, and I'll put W1, W2, Wm. This is our radial basis function neural network. Now, it turns out that there are, and I'll start with this next time, these universal approximation theories that say that so long as you have a non-polynomial function here, you can approximate any input to output mapping with sufficiently many of these units. So if you have an infinite number of these units, you can approximate any function. And that's really important for neural networks because this is basically the structure of a modern neural network. This is what we refer to as an input layer. This is what we refer to as a hidden layer. And this is a single output, but I'm going to call it an output layer. And so when we start hearing about multi-layered neural networks, what they're referring to is this perspective here, where although I pitch the radial basis function, it's almost like a modification of a single neuron. In reality, it's actually putting multiple neurons together, where I have this funny activation function in the radial basis function and a bunch of them. And each one of them takes all the same inputs, and then they get collected into an output. And this is our modern neural network. And so we're going to use these terms from here on out: input layer, hidden layer, and output layer. And we'll talk a lot more about that next Thursday, or do this, in 2 days. So that's all I've got for you. I don't want to keep you any longer. Happy to stay extra or longer for questions, but otherwise we'll see you Thursday. See if there's any questions accumulated online. There's a question: if we don't increase the spread, is there a possibility for a point to fall out, not being part of any of these zones? It's generally assumed that the radial basis functions have infinite support or semi-infinite support. And so every point will have a representation. So if you just crank up the gain, then you'll at least see something. So every point is effectively a part of every zone, but it's just more a part of some zones than the others, and that's what adds those up together. So that's why we don't usually worry about increasing the spread. And how well do RBF do at predictive control tasks? Likewise, they are very flexible, and so certainly you can find applications of our radial basis functions in control applications and predictive control applications and predictive coding, all sorts of things like that. So yeah, if you were just, these are fundamental neural network structures, so you'll find them being used all over the place. Extremely flexible, general function approximation tools. All right, any other questions online? All right, in that case, I will go ahead and end the call, and we'll see everyone on Thursday.